Thank you. So today I am going to give a short introduction to LiquidHaskell, and I'm also going to support this claim that I have been making recently that theorem proving is for all. And when I say for all, I mean for everyone in this room or for all Haskell programmers. Because the goal of LiquidHaskell, one of the goals of LiquidHaskell is to basically allow people to prove theorems within Haskell. So before we go to the theorem proving part, let me describe how LiquidHaskell works. And what LiquidHaskell is, it's basically, it takes Haskell, it starts from Haskell, and it extends it with these refinement types. So let's see an example here. I have this Haskell function take. Take takes as input a list, any list, and then an index I, and it returns the I first elements of this list. So if, for example, I take 2 elements from the list 1 to 3, then I return a list that contains 2 elements, 1, 2. But if I take 500 elements from the list 1 to 3, the result of this function call is not really specified from the type of take. So to deal with this non-specified behavior, I'm going to take the Haskell type of take, and I'm going to extend it with refinement types. So basically, I keep the Haskell type, and I put this blue logic inside the type. And now I have a refinement type for take that says take takes as input a list x's, and then a Haskell integer I. But also I use this logic to say that I is always less than the length of x's. Now with this refinement type for take, if I go and take 500 elements from a list that contains 3 elements, and I run this code with this refinement type specification in LiquidHaskell, I'm going to get back a refinement type error. Can you hear me now? Nice. OK, so today I'm going to tell you how LiquidHaskell works, how it does static checks so that you have both fast and safe code. And then I'm going to show you a short application, how you can use LiquidHaskell to speed up a parsing function. And then I'm going to talk about theorem proving. So let's see how this static checks works. So you also know that Haskell is already a very safe language. So it's a functional programming language, and it uses on the back all this theory of strong typing and lambda calculus. So it's already very safe, and there is the saying that if your program compiles, nothing go wrong, right? But this is not really true, because Haskell is also a practical programming language. So many times users want to have fast code, so they end up having fast memory operations. So for example, they use on the back C wrapper functions, so you can always go and have memory overreads in your nice Haskell code. And a very famous memory overread bug is this heartbeat bug that appeared 2015 in OpenSSL protocol. So how many of you know what heartbeat is? OK, most of you. So let me go very quickly through Heartbleed for those of you who don't know it. So I'm using this XKCD comic for Heartbleed. I have a user. I have this server. The user asks the server to store a warp potato. The server stores the warp potato. And then the user asks for the 6 letters of the warp potato. And the server gives back the 6 letters of the warp potato. Then, in the next attempt, the users ask the server to store the word bird that contains 4 letters. So the user comes in the memory, stores the word bird, and returns 4 characters of the word bird into the server. And then the user understands that something fancy is happening. So what it does, it says, take the word hat and give me back the 500 characters of the word hat. So the server stores hat somewhere and returns hat and the 500 minus 3 characters that are in the memory next to the word hat. So the server returns to the user information that the user is not supposed to see. And this is like how Heartbleed comes. And now let's go and see if we can actually go and encode Heartbleed into this safe Haskell programming language. So what I'm going to do is I'm going to use data text, fast constant memory manipulation library, and data text exposes this function that is called take that says, like the list take, give me as input a text t and index I, and I'm going to give you back the I first characters of the word text. So if I try to take 500 characters, as in the Heartbleed example of the word hat, I'm going to take a runtime error that says I cannot give you 500 characters of the word hat, and this is good. Like Haskell is safe here. I cannot go and encode Heartbleed. But if I go deeper into the take function, I see that what happens is the take is using an unsafe take function, and what it says is that if your index I is less than the length of t, then use the unsafe take function. Otherwise, throw a runtime error that says that you don't have the permission to do that. So this is safe, but it is slow, because every time I am using take, I am basically doing one runtime check. But it is safe, and we are fine. But if we want to speed up things, then we can go and remove this runtime check. And now our code becomes fast, but it is not safe anymore. So if I remove the runtime checks, and I'm going to take 500 characters of the word hat using this unsafe function that is exposed by unsafe text Haskell library, then I am basically encoded Heartbleed. I have a buffer overread, and GHCI is going to give you information that you are not supposed to see. So we don't want that, but what we're going to do instead is basically use these static checks. So I'm going to take this runtime check that take is using, and I am pushing it into the refinement types. So now I have a refinement type that says that the index I is always less than the length of take. And because this is provably at compile time, then I can go and remove this this runtime checks. And now I have a version of take that is not using runtime checks, and it is also like statically correct, because if I go and take 500 characters of the word hat and I run LiquidHaskell with this specification, I'm going to take a type error. So this is LiquidHaskell. It takes as input some code with some refinement type specifications, and it returns OK if the code is correct. Otherwise, it returns an error. And the way that this is happened is it basically it checks that all your arguments are valid, or your arguments satisfy your refinement type specifications under whatever facts it can collect from the environment. So let's go back to the Heartbleed example and see exactly how this happens. So I have my specification for take that says that the index is always less than the length of my input. And I am using X to bind the word hat. And then I'm going to take 500 elements from X. And what LiquidHaskell does when it sees this call is it is generating an implication. So specifically, it goes and collects whatever facts it can from the environment. And here the fact is that I have an X whose length is exactly equal to 3. And under this fact, I want to check if my arguments are valid, if the arguments of take do not violate the specification of take. And the way this happens is it checks that the actual argument of take, a value that is exactly equal to 500, is a good argument for the specification of take. And the specification says that this value should be less than the length of X. So I generated an implication, and I want to go and check this implication. And the checking happens automatically using an SMT solver. SMT solvers are black boxes. We treat them as black boxes. It stands for satisfiability modulo theories. And the idea is that if you give them logic implications from decidable logics, they say, yes, it's valid, or no, it's not valid. So in this case, I'm going to ask the SMT solver, is this implication valid? The SMT solver is going to say, no, it's not valid. And then LiquidHaskell is going to generate a refinement type error. And this error occurs exactly because my index is bigger than the length of the text, because I have this 500 here. So if, for example, I have a 2, an index inbounds, then the SMT query would be valid. So LiquidHaskell would report OK. Any questions? Yes.
What happens when you chain two takes?
Yes. Yes, if I change, if I, for example, take 2 from hat, this is valid, yeah.
But in the intermediate result is not valid.
There is, what is the intermediate result?
First, you take 500 from hat, which is a refinement error. But after that, you take 2 from the
Oh, yeah. So if I had, yes, the intermediate result would be non-valid, so LiquidHaskell would report an error for the invalid application. Yes?
What if the length is a value that comes from the user, a variable that comes from outside?
What if length?
The number of characters contained.
Oh, so the idea there is basically LiquidHaskell is abstracting information. So if I didn't have specifically this hat over here and I had a variable, then I need this variable to be refined with a type that gives some information about its length. So I can have not a string here, but something else. But LiquidHaskell would ask, what facts do you know about this variable of this something else? And it's it can generate an error if your code is correct, but the fact that it knows about the code is not enough. OK. Yeah, so LiquidHaskell takes code with specifications, and it basically checks that all the arguments are valid. And the interesting thing is that all the checks happen statically. And this is cool because I have here a diagram. On my x-axis, I have unsafe and safe code. And on my y, I have the efficiency, how fast your program is. And if I have static checks, then these static checks do not have any effect on the runtime, on the efficiency of your code. But they give me provably safe code. And as alternatives, I have runtime checks that, again, give me safe code. I can use runtime checks to beat Heartbleed. But then your code becomes less efficient. And another alternative is to have no checks. I have super efficient code, but it may go unsafe. So we saw how LiquidHaskell works, how it can be used to have static checks that give you both fast code because they're not used at runtime, but also safe code. And then I have this example. How can you use LiquidHaskell to speed up a parsing application? So let me go to a demo. So here I have a user datagram protocol data type in Haskell. And this data type has 4 fields. Each of these fields is a text that has 2 characters. And here I have a function, UTB parser, that takes as input some text and converts it into a UTB data structure. So what I do, I take my input text, and then I split it at 2 to take my first field, UTB1, and the rest of the text T1. And then I split it again at 2, and I do this 4 times to get all the fields of my data type. And here I have my split at function that is saved using this runtime check. It says split at, says give me an index I, and give me a text, and I'm going to first do a runtime check to see if I can actually go and split at the index that you are giving me. And if I do, I am using the unsafe version of split that is basically going and doing constant manipulation of the memory. So if I press this button, I am calling LiquidHaskell, and LiquidHaskell is going to generate an error. You cannot see here, right? OK, so LiquidHaskell is going to generate an error because it says that the error comes from the red of the LiquidHaskell, and it is generating an error at the error because it cannot prove that the error is dead code. It cannot prove that I cannot reach this point over here. So what I can do to fix this error is I can go and give a refinement type for the split at function. And this refinement type basically says that give me an index I, and then give me a text T, and I have to prove that the length of this text is always greater than or equal to the index I. So I is less than or equal to the T length of T. And now if I run this code, if I run LiquidHaskell again, then the error disappeared. because LiquidHaskell now can prove that this runtime check is always safe, so I am never going to reach my error case. Make sense? Yeah, so since I have this proof statically, then I can just go and basically remove my runtime check. And now I know statically that this call to the unsafe is safe, so I don't need to run this extra runtime check. So split.at is safe, but now it has this precondition. So if I go back to my UDB parser code, then I have errors. I have liquid errors, because LiquidHaskell cannot prove that this t over there has length that is always greater than this 2 that I am doing over here. So how do I fix that? The length of the text has to be greater than 8. We can do that. So I'm saying that I am giving you a text, and the length of the text has to be greater or equal to 8. And I have to close my comments. So LiquidHaskell is happy for the first split.at, because 8 is always greater than 2, so it can figure out this. But then it cannot prove that T1 has length that is greater than 2. Because split.at says, give me an index I, give me a text with this precondition, this assumption, but it doesn't say anything about the result of the two texts. So LiquidHaskell does not know anything about this T1 over here. Make sense? Okay, so how can I fix that?
Say that the result is t minus the length minus I.
Yeah, say that the result of split.at is a pair, and the right side of the pair is a text whose length is equal, the right, t-len of text minus I. Right? And yeah, now LiquidHaskell has all the information that it wants, and it can do the math. It is doing all the linear arithmetic on the back, and it proves that actually the code satisfies the specification of split.at. And if you want to take it one step further, you can come and refine the data type, the data definition of this UTB. And this is like when we use LiquidHaskell to verify code, this is always the case. Wherever you see comments, you just put these comments. When you see comments in English, you can basically take these comments and put them in your refinement types. So what I can do here is I can say that I'm going to give a refinement specification for the UTB data structure, and that basically encodes this information that I have over here. So I'm saying that the first field is a text, and the length of this text is exactly equal to 2. So now I don't need to have these comments anymore, because I'm using these liquid comments to express all the specifications. And now I can run LiquidHaskell, and if I run now LiquidHaskell, LiquidHaskell is going to check that every UDB that I am using also satisfies the specifications. So if I press this button, is it going to be red or non-red? Red. It is red. You cannot see. It is red, and this red basically means that you are generating a UDB, but you told me that in UDB, all the text has length exactly equal to 2, and I cannot prove that, right? And the reason why I cannot prove that is that I know that if I split 2 from something, I'm getting back a pair. I know information about the right element of the pair, but I know nothing about the left element of the pair. So how do I fix this error?
T-len of the first element of the pair is equal to I.
The first element has a len that is exactly equal to I.
It's TR, right?
TR, yes. And now I fixed everything. Yes.
How does it know the unsafe split out satisfies the spec?
Can you repeat?
How does it know that unsafe split out satisfies the specification of split out?
How do I know? Oh. So unsafe split out is an imported function, and it has these specifications.
Yeah, but how does LiquidHaskell know that?
Because I have a type, a liquid type for split out that says that these specifications are satisfied. Because I told it.
Okay.
Yeah, and this is again, like LiquidHaskell only knows whatever you put in the type. So if split out was not specified to have these specifications, then I would get a type error. Other questions? Yes.
So basically, you just assert that this property is true, and you don't actually prove that to LiquidHaskell. You just
For the unsafe split out.
yes.
Yes. For the unsafe split out, I assume this post condition. Yes.
So do you have to write those specifications for all the functions that are imported in this line, or can you at a certain point say, I trust that this is binding by this specification, don't go further?
So when you're using imported functions, you have two options. Either you import the specifications that come from the imported functions, and in this case, like unsafe split out imports this concrete specification, or you can use assume. There is a keyword that says assume that this imported function satisfies this specification. And this is like very common because usually like when you are using LiquidHaskell for a code base, then you are imported functions that are not checked by LiquidHaskell, so you can make any assumptions you wish there. And again, like LiquidHaskell will say safe, but assuming that the imported functions satisfy the specifications. Yes. Yes.
Do you have a code example for a function consuming unknown user input, doing a runtime check, and emitting values which have types which are refined, so we can see to how to establish the text and the boundary of our system?
Do I have an example that I am consuming input? So.
To establish this text in refinement types about data we are getting from users, and we don't
Oh,
know what they think.
data that we are getting from users. So, okay.
Some kind of runtime check.
Yes. So, yes. So assume that I don't have this assumption about my parser function. So an alternative that you can do is basically come and say if 8 is less than or equal to the tlen of t, then do that. Do adjust UDB, else return nothing. So you can as well have so you can very well have runtime checks instead of refinement types. And this is like a nice example where runtime checks pass information to refinement types to continue doing your static verification. Does this answer your question?
Yeah.
Okay. Yes.
Where are functions like tlen in this defined?
So tlen is a Haskell function. And there are in LiquidHaskell, there are two ways to lift Haskell functions in your logic. If Haskell functions are defined in one algebraic data type, you can use a keyword that is called measure, and it does all the reasoning for you because functions that are defined in one algebraic data type are easy, and SMT solver knows how to reason about it. And if it is like fancy functions, we'll see later, you use something that is called reflect. And then it says you can use reflected functions in your logic, but then you have to do all the reasoning yourself.
You have to do what yourself.
To do all the reasoning yourself. And I guess I can go to reflection, and you can ask me later. Yes.
Can you apply split out to an infinite list? It seems that LiquidHaskell is assuming that Haskell is strict. Is that correct?
Yeah, LiquidHaskell assumes that your language, there is the implicit assumption that everything you write is strict because there is a termination checker on, which means that everything that you type, LiquidHaskell tries to prove that it terminates, and if it doesn't terminate, then you get a termination error, which means that if you got a termination error, then you got an error, and you are losing this assumption that everything is strict. Okay, let me go back. So yeah, like we used LiquidHaskell to have code that is provably safe, statically safe, and it's also fast because like we can use all these checks to eliminate runtime checks, and all the verification happens automatically for you using this SMT solver. And a question that often arises is, like, using this SMT solver, how expressive can you get? Which takes me to the expressiveness part of the talk. And my claim is that you can do like very expressive theorem proving using this LiquidHaskell. So I'm going to start from a very simple theorem, and this theorem is taken from Graham's book, Programming in Haskell. And in this book, there is a section that is called Reasoning about Haskell Programs. And basically, we ported all the theorems of Graham's chapter in LiquidHaskell. And today, we're going to see two of them. So in this first theorem, what I'm stating is that for any element x, if I reverse a list that contains exactly one element x, I get back basically the same list, the list that contains exactly one element. And if you look at Graham's book, then you are going to see this proof that starts from the left-hand side and is basically applying some equational reasoning steps by applying reverse on the list, and then applying reversed on an empty list to get back an empty list, and then I am applying append on an empty list. I am removing append, and I am getting on the right-hand side. So my theorem is proven. So the problem with this proof is that it is a pen and pencil proof, which means that it's not machine checked. So any proof is a good proof. So what we're going to do now is we're going to take this proof and port it into LiquidHaskell. So I'm going to use refinement types to express my theorems. So I start from Graham's pen and pencil theorem that says reverse a list with an empty element gives me back a list with this one element x. And I am writing a refinement type to express this theorem. So in my refinement type, I'm saying for each argument x that is of type A, I'm going to return a Haskell unit value. I call it v. And this unit value is refined with a property that says that if I reverse a list that contains exactly this element x that I have as my argument, I get back the same list. So basically, I pushed the theorem in my refinement logic. And this equality over here is SMT equality, because LiquidHaskell is using SMT to prove everything. So I am assuming basically that the Haskell equality that I am dealing with satisfies all the axioms of the SMT equality. If your equal instance does not satisfy these axioms, then you can break theorem proving in LiquidHaskell. So I am just simplifying this unit value away because I don't use it. And then I go back to my theorem, and now I have expressed my theorem as a refinement type. And now I also need to express my proof as basically something that relates to this refinement type. And hopefully, Kari and Howard have given an answer to that like many years ago, and they said that theorems can be expressed as types and proof can be expressed as programs. So here I have my theorem expressed as a refinement type. I give a function this refinement type, and based on Kari Howard, what they said, what I'm going to do is I'm going to use a Haskell function, singleton-p, to express this pen and pencil proof of the theorem that we had before. So how do I define this Haskell function? I'm basically going to translate the proof that I have here as a Haskell expression. So I start from the beginning. The proof starts from the left-hand side. I have reverse x. This is a Haskell function, so I am good. And then I am at the point that I need to express this equality in a Haskell term. So how do you express this equality as a Haskell term? So I'm going to define a Haskell function equal dot, this blue Haskell function, that basically takes an input x, a y, and it just returns y. It doesn't do anything fancy in the Haskell definition. But its type is interesting. I'm using refinement types to say that equal dot takes a value a that I name x. And then the second argument takes a y. And also I have this proof obligation to prove that x is equal to y. And if I prove that, then equal dot returns a value v that is of a. And also it returns a proof in the refinement logic that whatever I return is equal to both x and y, so that I can continue using this equational reasoning to continue my proof. So if we go back at the proof, I use this equal dot. So now I am just continue to translate the pen and pencil proof. But now this equal dot basically has this proof obligation to prove that my two steps are equal. And this proof obligation continues. So when I reach at the end of my proof, I basically have a proof that each equational step is equal. So in all, I have a proof that the left-hand side of the theorem is equal to the right-hand side of the theorem. And with these steps, I am persuading LiquidHaskell and the SMT solver on the back that this is an actual proof. And then I just need to go and close my proof. So I have this QED operator over here. How do I encode that? So I just define a data type. I name it QED that has one data constructor QED. And I define this function, star, that takes anything that you want and a QED and returns a unit, because in LiquidHaskell/Haskell, all my proofs have type unit. So if I come here, I already have my proof. So I say star QED, which means that take this proof, give it to the SMT solver, persuade that all your steps are equal and enough to prove the theorem, and also convert all this to a unit value. And this is how you can do theorem proving in Haskell. Question? Yes?
Do more complicated things like induction?
Yes. Oh, yes, I can. OK, let me show you how I can do induction. So before induction, all your proofs are basically functions. So what you can do is you can go and apply your proofs. And if, for example, I go and apply my singleton P proof to 1, I go to my theorem and I instantiate x with 1. So I have a proof that says if I reverse an element, that a list that contains exactly 1, then I get back a list that contains exactly 1. So every time I apply a proof to concrete arguments, basically I am instantiating this theorem. And I can use these instantiations to prove more complicated stuff. So for example, here, I want to prove that reverse a list that contains 1 is exactly a list that contains exactly 1. And what I do is I start from the left-hand side, I conclude to the right-hand side, and in the mid I use this question mark operator where I instantiate my previous theorem. And this question mark operator basically says, take anything, instantiate it, take a theorem, instantiate it, and I'm going to use this information to give it to the SMT solver to persuade that my equational step here is valid. So I go from the left-hand side to the right-hand side using whatever I instantiated to this question mark. So what we saw is that you can use basically Haskell to reason about Haskell programs in Haskell. And we saw these three basic equational reasoning operators. I have equal dot to prove intermediate step. I have question mark to call theorems, to instantiate theorems. And I have things to convert Haskell proofs into unit using this star QED. And using these operators, I can encode theorems in Haskell, and I can check them in LiquidHaskell. And now we go to like, how about more interesting theorems, like inductive proofs. So I'm continuing on Graham's book, and I am going to a proof that he proved using induction. And the theorem here says that if I reverse twice any list x, I get back the same list x. And this is the pen and pencil proof that you don't have to read, but you can trust me that this is the proof I took from the book. And the question now is, how do we convert this proof into a liquid Haskell proof? So my first step is to define a recursive function, because I want to encode an inductive proof. So I define a recursive function that I call involution proof. And basically, in my base case, I define this function on the empty list. And in my inductive case, I define this involution p function on a const list. So my second step is to use these equational operators that we defined before. So I'm basically going to replace equal with my equal dot, and then I am just using QED to close all my proofs. And then my third step is to define limata. Whenever I am using limata, I am going to use function calls. So for example, this equality over here holds because of the singleton p property that we defined before, instantiated on X. So in this step, I am just going to take this comment of the paper-intensive proof and translate it into a function call of the singleton p property using this question mark operator. And so what is interesting here is that my inductive hypothesis is basically a recursive call. So this step holds because I'm calling the theorem that I'm trying to prove on a smaller list. So basically, it's my inductive hypothesis. And I am calling it using this question mark. And the question that arises is, like, is the proof well-founded? How do I know that, like, my proof isn't just a recursion that is unlimited? So let's go and see this proof in practice and how LiquidHaskell checks well-formedness and all this. So I have my LiquidHaskell file that is a Haskell file. I am importing equational that has all these blue properties that we saw. I have all these flags. This is an interesting flag and says that I am going to do, I'm going to check that everything is terminating using structural induction. And I am defining the functions that I'm going to prove properties over. I'm defining list append and reverse, and I am reflecting these functions into the logic. And this means that you can use reverse and list append into the logic, but you have to reason yourself about this. So the logic does not know anything about reverse of append unless you go and open up these functions. And here is the involution property, involution proof as shown in the slide. So my theorem is expressed as a Haskell, as a refinement type that says that for every list x's, if I reverse x's, I get back x's, and my proof is a recursive Haskell function. And here, for example, I have this inductive, this recursive call for inductive hypothesis. And if, for example, I go and make a non-well-founded recursive call, then LiquidHaskell hopefully is going to generate two errors. The first error over here says that if you instantiate involution property on x-axis, this is not enough for me to prove that this step holds, because like this step holds because if I instantiate involution property on axis. And then I get a second error up there, and we can see this error, and this error says that your function is not terminating. So if the function is not terminating, the proof is not well-founded, so like it's not a good proof. So I can go and turn this back to axis, and LiquidHaskell will be happy with this proof. And another thing that we need to check so that my Haskell function is actually a well-founded mathematical proof is that it is defined on every input. So if, for example, I go and not define the property on the empty list, then again, LiquidHaskell will generate an error. And this error says that your function is not total. So I check termination, I check totality, and Haskell does not have any other effects, which means that this is a pure logical proof. And this proof is using lemmata. So I have my inductive call with a question mark. I have singleton property that we saw before. And I also have a distributivity property that I am proving later on. So this proof is a fine proof. Everything works, but it is very verbose. And for some reason, people in theorem proving communities do not like big proofs. So we have a tactic implemented something like a tactic that is basically called proof by logical evaluation. And if I say prove this involution property using logical evaluation, what I can do is I can go and get rid of all the steps that don't involve explicit calls of other lemmata. So I can say that in my base case command, it's trivial. Go and do the unrolling, do logical evaluation yourself. And then I can say in my inductive case, I am going to use like this lemmata. I'm going to use distributivity. I'm going to use involution and the singleton property. And basically, I'm saying to LiquidHaskell, use this lemmata and do all the evaluation you can so that you can prove the property yourself. And this is a valid proof. And to make sure that LiquidHaskell works, for example, if I try to prove a wrong theorem, then hopefully it is going to generate a type error. Let me take this back. And yeah, so the proof uses this distributivity property that I have proved here, using, again, logical evaluation. And distributivity uses associativity and left identity that I have proved here. For example, associativity says that if you have 3 lists, x's, y's, and z's, and you want to append them, then the order of append is not important. You can first append x's with y's and z's, or you can first append y's and z's, and then append. You can first append x's and y's, and then z's. Any questions? Yes?
So this check for totality, is that something implemented by LiquidHaskell, or does it offload it to SNT solver?
So that's a very nice question. So when you're writing a non-total function, then basically GHC goes and inserts checks. So if I write involution without the base case, then GHC automatically will insert the base case and will say that in the base case, call an error that your function is not defined in this case. And this happened by the SNT. So what LiquidHaskell does is basically it is going and using all these functions that SNT is using to complete your cases, and it is inserting a false precondition to these functions.
So that's for the case when you have a partial function. But if you have if it's defined over all its inputs, but like in your previous example, you did involution P on a growing argument, where if you now append x to x's again, who does that checking? Is that the SNT part, or is that still LiquidHaskell?
If I append,
If you const x to x's and your call to involution P, then it's also not.
oh, this is yes. So termination checking happens by LiquidHaskell. So in this case, because we said it at the beginning, we had this flag, it is doing structural termination checking. It is checking syntactically that your recursive arguments are decreasing. But by default, LiquidHaskell is doing something that is called semantic termination checking. And you can come, you could come and say, this function is terminating because the len of x's is terminating. And we call this termination metric. And in this metric, you can have any logical expression that you want. And this logical expression that you write using this syntax should just decrease at its recursive call and always be a natural number. And this happens so LiquidHaskell right now doesn't know that it's doing theorem proving. So this is checks that happen by default to your Haskell code when you're running LiquidHaskell in them. Yes?
It's a bit of a stretch, but now that we have this property proven, can LiquidHaskell use that to eliminate 2 recurses into the list itself in running code?
It would be nice, right? So it's interesting because GHC has all these rules. So I think it is quite easy to just take theorems like these and make them into rules and say to GHC use them. Or the other way, like if you have rules, you can use LiquidHaskell to prove these rules. So right now you can do this, but you have to do it manually. I mean, the goal of doing all this is at the end to help the compiler do optimizations. But right now it doesn't happen automatically. Other questions? Yes.
Is it possible to do proofs about partial data or infinite data?
So liquid.
This wouldn't hold if you had an infinite list.
Yeah, LiquidHaskell right now does not let you generate infinite data because it has termination checker on. So there is no reasoning right now about productive or infinite data. Yes? You want to specify that your list is ordered. Yeah, so we saw in the previous example, I could do that. Huh? So we saw that if you define data type, you can go and use refinements on this data type. So for example, I can go and define a data list of A's that is either empty or a cons of A and a list of A's. And I can come and basically refine this and say that in my cons, I have my head that is of type A, and also I have my list that is a tail, and then I can come here and say, yeah, the question was, how do you define ordered lists? And I can come here and use refinements in my list data type, and for example, say that each element of my tail has a value that is this v is less than or equal to the head. And this is how you can define sorted ordered lists, because you can just go and refine your data types. You can do it to an existing data type. So yeah, it is like, I guess I can answer this offline. There is a way to define sorted Haskell lists, but ask me later. Yes?
When you turned on the PLE, is that kind of getting LiquidHaskell to try and work out induction schemes?
No induction, no external function code. PLE stands for proof by logical evaluation. So the only thing it is doing is it's evaluating whatever it can. So like here, it knows that X is the empty list. It knows that if I reverse an empty list, I get back an empty list because it's one step of evaluation. So then it knows that it can, again, reverse an empty list. Second step of evaluation, and it is doing only evaluation. You have to do all the case splitting and external theorem calling manually. So let me go to a last application of LiquidHaskell. And in this application, basically, we are going to use this equational style of theorem proving. But at this time, we're going to do it to use it to optimize functions. And the textbook example of function optimization is how do I optimize this reverse function? And by optimizing reverse function, I basically mean to make it to generate a tail recursive function. So LiquidHaskell right now cannot prove anything about the speed of the functions, but what it can prove is it can prove that two functions do behave the same. So what I'm going to do right now is I'm going to define a reverse up function, basically the accumulator in the tail recursive definition of reverse function. That is, reverse up is a function that if I call on x's and y's, it returns back a list, this, that is equal to reversing x's append this y's. And like right now, I am defining reverse up exactly as its specification. And I can ask LiquidHaskell, can you prove that reverse up satisfies the specification? And it basically says, what are you asking me? Of course, I can prove that. But now I will go and make like, and start like playing around with the definition of reverse up. So here I'm saying that if I call reverse up on the empty list, then this is equal to calling reverse on the empty list and then appending it to wise. But I can say LiquidHaskell, this is exactly equal to reversing an empty list is equal to the empty list appended on wise. And this is equal to just wise. And I again come and ask LiquidHaskell, can you prove that this is correct? It says yes, which means that reverse up on the empty case is equal to wise. And then I have my inductive case that I just like start by defining reverse up as its specification. But here I can again go and use this equal dot to play with the definition of reverse up. So I am saying, yeah, so for example, if I come like here and define reverse up like this, LiquidHaskell will generate an error and says something is wrong. I cannot prove that this definition of reverse up satisfies its specification because here I have reverse of x axis appended to y's, and now LiquidHaskell is happy again and again. Like happy means that reverse up satisfies its specification. And now I can come and play with the inductive definition of reverse up and say that if you reverse x cons axis, then this is equal to reverse axis and append to x. Can you prove that? And it will say yes, hopefully I can prove that. So now I have two appends, and I can come and change the order of these appends. So I say reverse axis appended to x's and x appended to y's. And LiquidHaskell say I cannot go and prove this step. Any ideas how we persuade LiquidHaskell about this step?
Using associativity?
Yeah, I can go and use associativity. Again, LiquidHaskell is not guessing theorems for you, but I can go and say, okay, use the associativity property on x's, the empty list, and y. Oh. Reverse axis, x, and y's. So now it can prove that. And now we see that basically now I have like the right-hand side of reverse up. So I can go and say, okay, this is equal to reverse up on x's and empty list x, y's. And now basically I have this definition of reverse up, and I got rid of the slow reverse. So I have my reverse and append slow version, and I have proved that all these equational steps that I used preserve this property of reverse up. And like this is cool because my function satisfies the specification, but like the last line of this function is actually the definition that I want. And the funny story is that when we reach this state of this equational reasoning for function optimization, basically I contacted Joachim and I was like, okay, can I use a plugin or a template Haskell to make sure that at runtime I just have these last lines of function optimization? And what Joachim said is like, you don't need to, because like GHC is very smart. So if you run GHC with optimizations on, like all these intermediate proof steps are going to disappear, yeah.
Is there a missing step at the end? You need to eliminate the append for a cons?
I can do that. You can say this, right? And here, right? Okay. Yeah, and like my goal was just to remove reverse. But yeah, what is cool is that if I give this function to GHC, with optimization shown. GHC is smart enough, and it is just going to see the last 2 lines of the definition, because it knows that equal dot is defined to just preserving the second, to just return the second argument. So it is just going to ignore all the intermediate proofs from you at runtime if I run it with optimization shown. Ah, okay. Yeah, this is yeah, not what ZTC is, but it still is ignoring all the. This is why we need to do all this automated, because when we are just copy and pasting stuff, I am making mistakes. Yes.
In the previous slide, you were telling LiquidHaskell to use the associative property of appending lists together.
Why am I saying it?
Why doesn't LiquidHaskell build it? Yeah.
Why it cannot understand this?
Yeah. No. Why LiquidHaskell doesn't have a built-in associative property of appending lists? Just totally very.
Oh, because like the question is why I need this and why doesn't LiquidHaskell by default know that associativity holds? And the answer is that append is a function that I defined append is this user-defined function. So LiquidHaskell cannot know properties about every function that the user writes, because like this is a super undecidable problem that it is not trying to solve. Yes? So the question is, does LiquidHaskell know that append is associative? And right now, LiquidHaskell doesn't know anything. It's just checking. The only automation that exists is this proof by logical evaluation that is doing evaluation. So it knows, like we taught it, how to evaluate. And the question of what knows by default is like an interesting question that, like, hopefully I will explore. But right now, it doesn't know anything. Yes.
Well, mappend isn't necessarily associative. It's associative assuming you've proved it because you've got some type class that says mappend equals whatever, and you've proved that's associative. Can LiquidHaskell, can you do the same thing you have there, put refinement types in the type classes? Is that a thing you can do to actually really enforce that proof obligation on the programmer?
So it's interesting. Right now, you can use LiquidHaskell to prove, to specify refinements in type class definitions. And like this is cool because, for example, you can define monoid, the monoid type class, and then extend it with like theorems that have this associativity and other laws that monoid hold. There is some engineering effort how to prove these things because of all this type class resolution. You can prove properties about instances, but you have to prove them right now. And like I am actively working on how to persuade LiquidHaskell that instances satisfies theorems that are defined as class laws. So like you can do it, but maybe like you need to do some engineering yourself manually. Let me close it. So yeah, like reverse up has this property that we saw. So you can basically use reverse up and persuade LiquidHaskell that if you use reverse up, you can define a reverse prime function that behaves exactly like reverse. And if you liked these examples, you can go look at our paper. So this paper is called Theorem Proving for All, appeared at Haskell 18. And basically what we did, together with Graham and Joachim and some people from University of Maryland, we took Graham's chapter on reasoning about programs, and we used LiquidHaskell to mechanize all these theorems. And what is interesting is that an undergraduate student did all these proofs. So like my claim and the claim that appears in this paper is that if you have pen and pencil proofs, it is quite easy to port them in LiquidHaskell. And then there is another paper that is called LWeb to appear at POPL 19. And here, like, we used LiquidHaskell to prove more interesting theorems. So in this paper, we proved a non-interference property of a Haskell application. And non-interference basically means it's like a security property. And it is a very complicated property, but like it took us a lot of time to formalize this property in LiquidHaskell. But this is a feasibility result. So you can use LiquidHaskell to prove fancy theorems. But the problem there is that there is no interaction. So like, it's not like Coq or other proof assistants that if you get stuck, help you and tell you what to do. So if you get stuck in LiquidHaskell, then you need to figure out the next steps yourself. But my claim here is that LiquidHaskell can be used for theorem proving, not assistant yet, but you can do theorem proving, and you can do theorem proving on top of all this static verification and checks that you can use in your application to eliminate all these runtime checks. And with this, I want to thank you.
Yes?
If the type classes in base, like the famous ones like semigroup and monoid, were tagged with these properties, could LiquidHaskell be used to check that the instances are law-abiding?
So
Like for lists, for example?
So right now, what you can do is you can use refinement types on the type class to define these properties. And then when you are using these type classes, you can actually use the theorems of the classes. This is already implemented. And the other bit that is implemented is like, if you have lists, you can prove theorems about lists. What like LiquidHaskell is not doing, because of engineering right now that I'm trying to figure out, is how to define like instances and prove and persuade LiquidHaskell that the instances, like the syntax instance, the Haskell syntax instance is actually satisfying the class laws. But this is engineering because I'm trying to understand how class resolution works to persuade it that instances actually satisfies class laws. So like I hope it is coming soon.
Does LiquidHaskell make property-based testing with quick check obsolete?
So there is a mechanization that is called target that is checking properties that you define as refinement types using SMT. So there is no relation between quick check per se and LiquidHaskell right now. But there is another like tool that generates counterexamples or tests when your refinement types fail.
So in the example of take, you constrained the type so that you couldn't call it with an integer that was too large. But of course, the normal Haskell take function can be called in that situation, and you just get a slightly shorter list. So I wonder, is it possible to specify multiple refinements for a function, or what do you do in that situation? Can you sort of express conditional properties?
So you cannot specify multiple refinement types for one function, because then when you call this function, LiquidHaskell has to somehow guess which refinement you like, which type, if you use, your program is safe. So we don't allow that. But LiquidHaskell has an assume keyword. And like when you're type checking your file, you can say like ignore everything that you know about stake or about some function and assume that it has this type. So it will get whatever you assume, like, and ignore everything else.
So I'm wondering if you use, so you showed the example with take at the beginning, where you would get a performance optimization. But now if I were to use LiquidHaskell in, say, my library to do these checks and to do them at compile time, then of course, so what happens if now another person imports my library and they don't use LiquidHaskell? Then they don't get that safety, right? Or is there some maybe proposed compiler support where you say, well, if my library uses LiquidHaskell, I would at least get a warning or something. Because,
yeah, you don't have.
So
That's
GHC does not know the existence of LiquidHaskell. So if you don't use LiquidHaskell, then like all the signatures that you import is basically comments, and they're not checked. Like, yeah, they're totally ignored. So yeah, LiquidHaskell does not give you any guarantee if you are not using it.
Hello. I really enjoyed this interactive presentation, and I'd like to know how can I do one of my own? What tools have you used so that you can edit code in web page and yeah, LiquidHaskell it and
There is
and see the errors?
it's on my GitHub, like LiquidHaskell, a Liquid tutorial. So it's using JavaScript and Haskell for the implementation. Yeah, you can find it in my page.
Okay, thank you again.
Thank you.